Hey, Oren. Hey, Inger.
Hey, how are you doing?
Hey, well, good enough for the St. Petersburg spring weather, which is like a little bit cold here, but still fine for the conference time. Perfect weather. And what about you? It's early morning on your end, or?
It's same time zone, and we have a cold morning, so 25, 27 Celsius. 2 days ago, yeah. To be fair, 2 days ago we had 42 Celsius, and I don't know where I live it because it's not supposed to be this way.
Okay, when I say cold, it's like it was 6 Celsius this morning here, so
Yeah.
it's a little bit different. So, Andre, in the introduction, Andre told that you're, of course, famous for the RavenDB and the maybe, not maybe the only database written in C#, but at least maybe one of the famous ones written in C#.
Mhm.
And Andre also pointed out that the natural question is, why? How come did you decide to use C#, especially back then when it was not maybe the most performant language and the platform?
It's interesting. It's interesting because the language has an impact on what you can do, but it goes both ways. So if I was trying to write RavenDB in C or C++ or something like the standard database languages, the overhead of doing things would be enormous because I would have to handle a lot more than I needed to get started. By choosing a C sharp, I was able to actually get everything ready in a short amount of time. The first version of RavenDB moved from an idea in my head to a product in under a year, quite a year and a half maybe. But not. But at the time, I wasn't working on that on a full-time basis. Uh, and if you think about it, that's kind of amazing. Admittedly, the first version of RavenDB, we used an existing storage engine and we used an existing search library, but there was a lot of glue that had to be written that C Sharp made it a lot easier. And to be fair, while C Sharp isn't traditionally or wasn't traditionally a database language, if you look at managed languages in general, quite a lot of databases are written in Java. Anything from Cassandra to Hadoop to Zookeeper, Kafka. And the primary reason here is that in many cases, the performance of the language itself is not that important compared to the algorithm and approaches that you take. Now you have ScalaDB, which re-implements Cassandra in C++, and they are showing much higher numbers, but a huge percentage of their performance doesn't come from, oh, I'm running on C++. It's because they have their own custom IO stack, which helps them do a lot more things more efficiently.
Okay, so it feels like, yeah, the language is not the only and the deciding factor. It's a lot of different bits and pieces involved in the database performance, including the IO stacks and the hardware, maybe even on the
Yeah.
low end. Yeah.
Another thing to notice is that unlike Java in particular, C Sharp was created to have a really good integration with the underlying system. We're talking about things such as value type, unsafe code, pointers, a whole bunch of other things of this nature, which means that if you roll up your sleeves and get to work, you can get the same assembly running in C sharp in a critical in critical sections that is that you would generate from an optimized C++ compiler. but at the same time, I don't need to pay the cost of huge compile times, much more involved memory management systems. I can lean on the environment a lot more, and that means that in non-performance critical areas, I can move a lot faster.
Okay, great. So I think this is a very good introduction into the topic because it kind of highlights that there are many different important areas and aspects of when you design and try to write a database. And that's what you will be kind of talking about in the coming hour. So I would like to invite all the kind of attendees to join the chat and ask questions, and I will ask them in the broadcast right when you're asked, as we agreed with Oren. So if you want something to know, if you want to know something or you didn't understand something that was on the slides, then just ask right away in the chat and you will hear the answer almost immediately. And now, so let's go to the talk then.
Okay. So I want to reemphasize what Igor said. If you have questions, ask me immediately. This is a online presentation, and I miss having feedback from the audience. So this is the rough structure of this presentation. I'm going to talk a lot about the internal structure, how a database arrange the data, how it reads, write, operate on that, those sort of things. Then we're going to talk about some of the things that makes the database complicated, how we maintain durability, how do we create transactions. And finally, I want to talk about some of the neat tricks that gives you huge performance boosts. Now, I write databases for a living. And that means that, and the company is growing. We recently had, we hired 3 new developers. And my goal was to get people who are completely new, fresh from university, ready to start a career. And I asked them a question, which I consider to be a very, very simple question. I want you to build a persistent phone book. That's it. Name, the phone number, write it to a file, read it, stuff like that. And people failed. People not only failed, people failed in a horrible manner. And to the point where someone sent me, oh, here is a phone book implemented using SQLite. I'm like, yes, that's great, but I want you to know, want you to get to the point where you can implement SQLite. And the problem is that for many people, a database is a black box. It's unknown and unknowable about what's going on. And the purpose of this talk is to make sure that I open the box and show you where all of the pieces are, so you understand what is the database doing behind the scenes. I'm going to talk specifically about the kind of databases that I build, but I'm also going to touch on some other alternatives for the implementation choices that I'm talking about. So let's talk about what is a database. And a database is a way to store and retrieve data. It's critically important that we understand what is the format of the data. And the format of the data may mean, are we storing data in column major format, in row major format, stuff like that. This has impact on the kind of operation that you can have. A critical part of a database engine is resource management, balancing I/O, memory, CPU time, all of those sort of things. A database is a mini operating system in many respects. And finally, transactions, all of the ACID property, atomic, consistent, isolated, durable, those are things that we have to deal with, and they are non-trivial to do so. And finally, we not just store data, we want to also query that, hopefully in interesting ways. So this is probably the simplest answer to the persistent phone book that I can think of. Just store the data as a CSV. And that's work, and that's easy. However, as you can imagine, there are some disadvantages to this approach. So it's easy, it's human readable. A lot of people just click on that, it makes sense. But when I want to do a search on a CSV, I have to do a linear scan, an ON operation. An ON operation means that if I have 1,000,000 records, I have to go to 1,000,000 records to find a match. I can sort the data, but then I have to do a lot of random reads. We'll see that in a moment. Much worse, if I need to modify a record and the size of the record change, I have to rewrite the entire database. If the database is 100 gigabyte, that is not an option. Typically, when I'm talking to people about sorted data structures, and a database is nothing if not just all about sorted data structures, then they come up with trees, skip lists, a bunch of other stuff like that. And those are known optimal solutions. You can't get faster than that. There are proof on that. Go read Knut if you like that. Now, the problem with that is that there are hidden assumptions in those optimal solutions. And this is the key aspect. They assume that the cost of accessing any particular value is the same. And that's not true. That's not true in memory because we have L1, L2, L3, the cache line at the CPU level. Then we have main memory. But for a database that uses persistent medium, it's substantially not true. You can see some of the latencies here. For reading 4 kilobyte. And I want you to notice that the unit that we use change. 50 nanoseconds from RAM. 100,000 nanoseconds from NVMe. That's Intel Optane. That's the effective one of the best that you have. 500,000 nanoseconds from a enterprise class SSD. And 8 million if you're using a really, really good HDD. And that leads us to the interesting observation. 6 times is the major cost in data structures, in persistent data structures. Now, if I'm looking at a binary search tree, the cost of finding a value is O log n. The question here is, what is the cost of each operation? And a random read is one of the most expensive operations that you can have on a disk. So if we do the math, if I have 1,000 items using an AVL tree, 1,000, which is effectively nothing, then it's going to cost me 5 milliseconds on the SSD, 80 milliseconds on the hard disk. I move to 1,000,000, and the cost on SSD is 10 milliseconds to do one search. And that's absolutely insane amount of to work with. So we cannot do that. We need something else. And the answer to that is to stop thinking about the value, about the data in terms of individual bytes or sections or something like that. We're going to start talking about the data in pages. We're going to take the page, take the file and divide it into individual pages, typically 4 kilobyte to 4 megabyte in size. My RavenDB uses 8 kilobyte pages. And the idea here is that we are never accessing a byte. We are always accessing in the page level granularity. So when I need to read something, I've said, okay, give me page 6. And then I'm going and reading page number 6 from the disk as a single unit, 8 kilobyte in one shot. Now, this is interesting. Why is that? Because if I'm reading 8 kilobyte in a one shot, and then I can modify within that page as much as I want, And then I can throw that out to the disk again using an 8 kilobyte write, which means that the locality of reference, being able to pack values into a single page, is critical. Now, I'm going to take you back to 1979. There is a paper that is called the Ubiquitous B+Tree. So we are talking about 40 years ago, more than 40 years ago. And at that time, the concept of the B+Tree has already been prevalent. And this is basically because there is no other way to approach that. So the idea here is that random reads are really, really expensive. So let's avoid that. Let's keep that. Instead of getting one result each time, let's get a whole page which may have many results. But how does it work when we have a sorted structure? So you can see here that I have a page, and this page has 4 results. So I'm now going to search for the value of 256. I'm starting from this location. I did one read, and then I have these things. Now I'm going to say, okay, let's do a binary search here to 256. It points me to this. And now I can follow this to page number 4. And I do another 8 kilobyte read. And you can see that here is probably 256. Does it make sense? I mean, we just read 16 kilobytes from the disk. And the key here is that reading sequential data is fast. The cause is typically in the SIC. By the way, this used to be so important when we had hard disk, which had the actual rotation and needed all of those sort of things. Now we have SSD, we have NVMe, and that's still true. If you go and look at benchmark numbers, sequential read is still much faster, even with NVMe. Random reads is improved significantly, but seek time still matters. What is more to the point, the cost of random read is not that meaningful in terms of the size of the read. So if I want to say, hey, read 4 bytes from position X, or read 4 kilobyte or 8 kilobyte from position X, the cost is going to be effectively the same. Why is that? Because the disk doesn't deal with bytes. It deals with sectors, and sectors are typically in 4 kilobyte these days. So you're already going to read 4 kilobytes from the disk, however much of that you actually intending to use. So if you're going to work with the hardware and get 4 8 kilobyte page at one time, it's the same cost as reading 4 bytes. But now notice this, the search time that I have is not O log n, is O log f of n, where f is the fill factor. What is the fill factor? It's the number of entries that I can pack into an 8 kilobyte page. Let's say that I can pack only 100 items into an 8 kilobyte page. Just to give you some numbers, 8 kilobyte divided by 100 means that the average entry is 82 bytes, which is relatively large. In many cases, you will see 150, 250 fill factor, but let's assume that the fill factor is just 100. Look here. That's the time that it takes to do a search. And to compare, this is 26 that we have to do here, and 10 milliseconds, 800 milliseconds. Here, 5.6 for 1 billion entries. That's a huge impact. But notice that here I'm cheating. I'm saying the 2 millisecond, 4 millisecond in SSD. But there is another trick that we can play. This is the structure of a B+Tree with a fan out of 128 items per page. So the root page is 8 kilobyte. And let's assume that I have 128 items on the second level, which is 1 megabyte. And for each one of them, I have another 128 at the second level. So the total size of the second level is 128 megabyte. Third level, 16 gigabyte and 2 terabyte, blah, blah, blah. Now, let's talk about how much it's going to cost me to search a value. And it's going to say, okay, 1, 2, 3, 4, 5. So when I have a data set that exceed the 2 terabyte mark, and the number of items that I have here is insane, 5 disk 6 is enough to do the work. And this is exactly why B+Tree is such a useful data structure. This is why it's pretty much the core of every single database that you might think about. There are actually other ways to store data, but B+Tree is and has been the default for a very long time. Now, something that we also need to understand is that one of the strengths of the B+Tree is that it plays very nicely into the memory hierarchy in the system. What do you mean by that? Let's say that I have a cache of 128 megabyte. I'm going to say, okay, let's take all of those items, all of the pages in the first 3 levels of the disk, of the tree, and then I'm going to cache them in memory. What does it mean? It means that the cost of doing a search has been dramatically reduced. It used to take me 5, 6 to do this. I paid with 128 megabyte. And now it takes me 2, 6 because this guy is in memory, this guy is in memory, this guy is in memory too. And now maybe this and this I have to do a read to the disk. Even so, even if I dedicate just 128 megabyte for this, I can still benefit a lot because it's very likely that I'm going to have hotspots. So if I'm always touching in this area, then all of this is going to be cached. I'm going to have one disk all the time. Now, let's assume that I'm currently doing something that involves scanning through the B+Tree. So I'm going over here and then I'm starting scanning this direction. This is going to be fast because the items that the pages that we already went through are going to be memory resident already in the cache. And think about it, this is actually an insane level of performance that we get for very little cost. On the side, this also applies on the other side. We talked about a memory hierarchy in terms of caching things in main memory to avoid going to the disk. But the structure of B+Tree means that it also plays really well with things like main memory, L1, L2, L3, and that gives you a really significant boost. And notice these guys. With 1 billion records, 40 milliseconds, because I can optimize this on HDD. Now, one of the common issues with pages is that they fill up. And you might have heard the term page splits, and page splits are bad. So let's talk about what exactly this is. Here you can see a page that contains some values. The values in here are sorted. Now I need to insert a new value. Now, I have no more room in this page. I cannot do this. I need to create another page. So I'm actually doing that, and I'm moving. And this, in this case, this is a single page of a B+Tree, just has a single leaf value, and now I'm breaking it apart into two. Here is the old page, and this is the new one with just HANA and 6 empty slots that I can use. And now I have this thing that sits in the middle and direct me, oh, you're looking for Keynes, so Keynes must be between those two. Here he is. And notice that in this case, I probably didn't touch this at all. I just added new pages. That's great. This is what we want. However, let's go back and say that I need to insert Ben. Ben needs to go here. I cannot fit Ben here. So I have to split the page. But now I have a different problem. I can't just create a new page. I have to modify 2 pages. Notice that here I have 4 items and here I have 4 items. And I have empty space on both of them. So this will happen when I'm inserting data in a non-sequential manner. The pages break, and then I have empty space inside. Why does it matter? What's the big deal in that I have this empty space? Well, to start with, it means that I'm fragmenting the tree. It means that one item, one case I'm reading and writing here, the second I'm reading and writing here. Remember the memory hierarchy. I would have to bring more things into memory. The other thing is the impact on the tree. Here I'm adding data in a sorted fashion. Each leaf page has 2 items in it. And you can see that the height of the tree is 1, 2, 3. In here, I insert data in a random order. So I had early page splits. And you can see that the sum of the amount of data on the leaf pages is not balanced. For that matter, 1, 2, 3, 4. The height of the tree is bigger, deeper. And this is just one, but this means another seek. And as we mentioned, a seek is a huge cost. By the way, I'm using the term seek to refer to a random read from the disk. The other side that we have to understand here is that the more packed data, the better it is all around, because I'm going to do operations, and this one, the fourth level, the second level that I have here, I only have to pay 16 kilobytes to cache that. Here I have to pay 24. So that is a huge impact on the overall performance of the system. The point where in many cases you will see databases spending a lot of time pre-sorting the data. All of the bulk insert processes that you have, a key factor of their performance is that I'm going to read the data into some memory without trying to put it into the B+Tree, sort it, and then write it to the B+Tree as necessary. And it turns out that this has a huge impact on performance, sometimes order of magnitudes better. Now, another issue is what and how do I work with my B+Tree? And there are 2 typical ways of handling that. In the first model, and you can see it here, I'm embedding the data directly inside the B+Tree. So if you're talking about a database, the typical key would be the primary key. And in the leaf page, I would have the actual content of the record. Now, this has some advantages and disadvantages. The major disadvantage is that the tree is deeper. Why is that? Because at the leaf pages, we cannot fit as many entries because we have to reserve space for the actual record contents. The other option is this guy. In this case, we are storing the data separately from the B+Tree. And this matters because that means that I'm able to pack more details here. Now, the downside of this model is that I have to now do random reads to fetch the data itself. The advantage here is that I'm typically able to optimize that. I would read all of the values that I need, and then I would probably sort these details and read them, hopefully to the point where I'm able to get the optimal access path to the disk. So, for example, I would read this, sort it, and then read it in this fashion, in order, which is fast. If I'm doing here, when I'm reading from the B+Tree, I'm already here. I can give you the results immediately. So there is a cost benefit here. In SQL Server, for example, when you're creating a cluster index or a cluster parameter key, this is what this means. This also explains why a table can only have a single clustered index. Because a cluster index is literally how the data is stored on the disk. In many respects, I like to think about it as phone books. And some of you may have actually never used a phone book, but the idea here is that this is something that that makes sense in a physical fashion. It makes it a lot easier for people to understand what's going on. Now, in some cases, the record that we use is too big to fit in a page. Now, if the page is 8 kilobyte in size, then obviously if the value is 9 kilobyte, I can't fit it. But remember that a leaf page must be able to store the key and hopefully multiple keys. So in practice, the maximum size that we have is under half the size of the page. So in this case, if I have a value that is 4 kilobyte in size, we cannot put it inside of the leaf page. Instead, what we will do, we will allocate a separate page just for that, or maybe multiple pages. If this is a 17 kilobyte value, I'm going to need to allocate 3 pages to hold it. And then this is called overflow. And now I'm able to say, okay, I'm going to record it as a pointer outside of that. Talking about the large values. If you have a blob or a binary large object or character objects, those would tend to sit outside of the record. Okay. Now, let's talk about the internal structure of the B+Tree itself. And the basic idea here is that we have a 4 kilobyte page or 8 kilobyte page, and we have some metadata. And this is the floor and ceiling of the items. Now, as I'm inserting data into the page, I'm going to write the record here. Then and notice that there is absolutely no order here of those values. But the page is sorted. And what gives us the sort order is this thing. A, B, and D. That's the sort order that we have here. So effectively, the page is composed of 2 things. On the one hand, we have the user who is, we have the data who goes on the bottom, and we have the offsets to them in the top. Let's say that I need to insert C here, a value whose key is C. I would write this thing here, And then I would shift this one down and put C here. So this would be sorted. Now this go like this until they meet in the middle. When they meet in the middle, then the page is full and we have to create a split. Okay. Now, let's talk about what we can do with a B+Tree. And it turns out that we can do quite a lot. The simplest answer is that we can do operation by key. Give me item so and so. And that's great. But this isn't really that important from our perspective because we do that. It's a lot more interesting to understand that because the B+Tree is a sorted structure, we can do all sorts of tricks. Oh, I want to search by prefix. Let's assume that I'm building my phone book, and the entries that I have there are sorted by first name and last name. It's last name and first name. If I want to ask, give me all of the user whose last name is Smith, I can do that by doing a prefix query. Conversely, I can do a range operation. Give me all of the users whose names start from M to the users whose names start with Y. Now, it doesn't seem like that much of an interesting thing, but it turned out to be critical aspect for many operations that we have. For now, remember this: I'm doing a search on a B+Tree. If this is cluster, I already have the data. If it's not cluster, I have to go and load the related data. Now, so far I talked about B+Trees as the primary data storage mechanism. But B+Trees are also commonly used. So storing the data is something that you can do in many ways, in heaps, in arbitrary structures, whatever. What matters is when you need to query the data itself. And typically you do that by creating an index. Now, let's say that I want to create an index to answer this query. Order by register desk and name assigned. How I'm going to do that? I'm going to create a B+Tree whose comparison function is going to be this. Given two records, compare the registration date in a descending order, and if it's the same, compare based on the name. Now, here is the output. Notice that these two together are the key, and this is the location of the data. If you use stuff like that, you're very familiar with how it works. I'm searching for books by topic or by author name, and it tells me some details about them, and then it sends me to the bookshelf. Now, think about what it means. I want to ask a question. Give me all of the users who registered this month. How do I do that? Well, I can go and scan for all of the records that has this prefix or that are within a particular range. If I want to answer this query, all I need to do is walk the index and return the results in the index order. Now I can do the other way around. I can search using register ascending and name descending by doing this. But those are the only two options that I have. Register desk, I'm ascending. So I can answer these two using this index. I cannot answer these two. What's the problem with that? Well, it turns out that I can still do some things. I can say, you know what? I'm going to scan this index, but use only this piece of information. And then I'm going to have to sort myself at query time to compute this. There are ways to make it slightly more interesting, but that's roughly the way it goes. Now, notice that after we scan the index, we have to load using RavenDB. And RavenDB is a very important concept. But before we do that, I want to talk about a little bit about what scan versus seek mean. There are two ways in which we can use a B+Tree or something like that. We can say, give me a value using the key. For example, give me 2021 March 21 Emily, and it will find me this. Or I can say start from a particular position, maybe the start position, but maybe start from March 20 and scan up or down the tree. Again, sorted structure, that's it. If you're looking at query plans, you have to understand what's going on. If I'm seeking in index on a B+Tree, that is effectively a log operation. That's fast. If I'm scanning the index, that might mean that I'm scanning through the whole index. It's important to understand what's actually going on behind the scenes to understand how you can best utilize that. Okay. Now, let's talk about what is exactly a raw ID. And a raw ID can be one of two things. It can be a physical representation of the data. This data is located in offset X. Or it can be, oh, you need to look, this is the logical raw ID. I need to look up in another location in order to find it. Now, let's consider this query and consider the impact. I want to get, the top 100 items. So I'm scanning the disk, I'm scanning the index, and then I'm getting 100 raw IDs. And I can do ON operations to get them from the disk, or I might need to do nlog n operations because I have to do a query on each one of those on the map between the logical representation and the physical representation. Let's look at a real use case for that. Here is when we are using physical disks, physical raw IDs. So the primary index and the secondary index are all going to point to the location on disk. In this case, a secondary index is going to point to the primary index, and I have to go through that to get to the actual data. Uber, I think like 3 or 4 years ago, had an interesting post about migrating from Postgres to MySQL. And this specific thing was a major factor in their decision. Why is that? Because Postgres uses secondary indexes that point directly to the disk, which means that any modification of the record is going to need to update all of the secondary indexes. MySQL uses this method, which means that if the value on the secondary index didn't change, we don't need to touch that. It's already point to the primary key of the record, and we can use that. The kind of impact this makes is huge. Uber said, I want this to reduce the write load. I much prefer this model because this reduces the cost of scanning through an index and giving you the actual results that match it. Because I can very quickly say, okay, here are all of the raw offsets in the file that contain the data, let's go and fetch them. in the optimal fashion that I can have without doing additional computation. Now, a really interesting aspect. Most databases in the end are all about managing trees. And which means that find by key, prefix, and range are cheap if there is a tree that match that. It means that scanning by primary key or secondary key is really fast. Everything else is expensive. Why is that? Everything else requires you to make a computation. Let's go back here and say, something like this. I'm looking at that, and the database says, okay, I have no choice but to scan to each record, compute this value, which I have to invoke now each time for each row. I have to invoke now and compute this, and then run this. On the other hand, when I have this, situation is drastically different. Why is that? Because I'm saying now, assuming I have an index on birthday, now I just need to find a value that all of the values that are smaller than this. This is a seek to the sorted value and then just scan it from there. This is an O-log-n operation. This is an O-n operation, really expensive. This is cheap, trivially cheap in most cases. Now, database tends to be very fast, and they do a whole bunch of tricks in order to pretend that they can do more complex queries. But you have to understand that if you can utilize the indexes properly based on that, if you can utilize this shape of the data based on that, then you're golden. Okay. I'm now going to move to talk about durability. And durability is something that really, really, really is annoying. And the reason it is annoying is that you're pretty much forced into an unpleasant situation, really unpleasant situation. And the reason is that this sucks. This sucks so much. And it's interesting because why? And by the way, this is a hard disk, but I'm also referring to SSD and NVMe, and everything that you know about I/O is a lie. If I/O is just a complete and utter lie, it doesn't work the way you think it does, and this is why. L1 reference talking to memory is talking to the L1 cache in the CPU. This is 1 nanosecond. Talking to DRAM, 50 milliseconds. Talking to NVMe, 10,000 milliseconds, 30,000 milliseconds. But this is where I'm talking about read 1 byte. If you remember, I had earlier numbers for 4 kilobytes, which is slightly bigger. And this is this thing, which is not fun at all. Now, those are optimal numbers. No load, best case scenario, stuff like that. In the cloud, this is so much worse. Just to give you some number, in AWS GP2 disks, you can expect a latency of 1 to 1.5 milliseconds for random reads. GP3 disks can expect a latency of 2 to 3 milliseconds. That's insane amount of time to wait. Now you can go higher. You can go to IO2. You can go to UltraDisk in Azure. Those give you sub-millisecond performance. But remember, we're comparing to this. It's not that good. And because of this, we have to deal with a lot of annoyances. Let's look at this code. I'm going to give you a second to look into that and think what this is doing. I'm trying to have a durable write. By the time this code returns, I'm expecting that the data is there. I mean, that's what you expect it to do, no? It doesn't. It really, really doesn't. Why? Well, here's the issue. Because I/O is so slow, and by the way, a millisecond range for those sort of things is still amazingly good because it used to be hundreds of milliseconds. But this is still too slow. So there's a lot of buffers all the way down at every single level. Now, what this means in the end is that we are talking about, for the moment you made a write, to the moment the data is actually on disk, can be many seconds. Typically, it's greater than 30 seconds. Now, if you're saving, I don't know, if you're saving a document about an email or something like that, 30 seconds is usually not a bad idea. Okay, lost 30 seconds of writing the email. Big deal. If you're writing a database, that's the entire world. So we can't afford that. We have to find a better solution. So I did a little research and I found this thing. I need to do an Fsync. This forced the data to be written to the disk. I'm done, right? And the answer is that no, I'm not done. Because the I/O mechanisms are written by people who really want to make my life hard. Well, to start with, this can fail. This can fail. And even if everything passed successfully, things still can fail in all sorts of interesting scenario. A few years ago, there was the Fsync gate fiasco, where Postgres realized that Fsync can actually fail, and that would cause a lot of nonsense. I highly recommend reading these two articles. They are mostly the same, but they go into great depth into why I/O sucks. This is a recent paper that talks about how can applications, in this case applications are databases, recover from Fsync failures, databases and file systems. And the answer is that they generally don't. But just to give you some short intro on why this is hard, you open a file, you write to the file, you Fsync the file, assuming you know that you're checking all of the errors. You close the file. This is not done yet. Why? If you created a new file or if you modify the size of the file, that data does not belong to the file itself. That data belongs to the directory. So you have to open the directory and Fsync that in order to properly persist stuff. And I'm only starting to touch on the insanity that is durable writes, because there is another issue. I can't modify the data in place. What happened if I had a failure? I modify the data, I have some partial writes there. This is corruption. So I have to write to a secondary location first. And I have to write in a durable manner. The way that it typically works is that I have either a Rightahead log, and I'm going to touch on that a lot later, or I'm using the append-only model. The append-only model says that I'm writing only to the end of the file. So partial write there would just mean, oh, some data that I have to skip to find the real one. The problem with append-only model is that it requires compactions. And that means that at some point I have to rewrite the file, needs twice the disk space, etc. Now, the write-ahead log is a file that I can write to in a sequential manner. Remember, sequential manner is so much faster than random writes. I have to do that in a durable manner. And the way that it works, I'm writing to the log before I'm modifying the data file. Now, on startup, I have to read the log file and just decide what modification I have to do to the data file. So basically, I'm writing to the log, I intend to do X, and then I write it to the log in a durable fashion. The durable write to the log means this is the actual commit of the data. From this point on, I'm guaranteed that either I will apply the changes that happen, or in a crash, I will reread the log and write the data. There are two types of write-ahead logs. One of them is the redo log, which is let me, I'm writing the changes I'm about to do. And the other one is the undo log, that I'm writing what I need to write in order to undo the changes that I'm about to do. It doesn't actually matter that much. It's a matter of style. But it's a matter of style that is very important because of the protocol that you have. There are two ways to talk to the database. One of those is the chat. Open transaction, select, insert, update, let me think about it, commit. The chat model can take minutes to complete, which means that you have an open transaction running for a very long time. The other alternative is the message model. I'm sending you all of the operations that you need to do in one shot. It may be multiple operations, but there is no back and forth, which means that the time to run the transaction is typically much, much shorter. That has an impact if I want to do the undo or redo models. Because in the undo model, if I have a very long time, then it's typically cheaper to modify in place and says, okay, this is how you undo those changes. Okay, now actually writing to the log in a durable fashion. You can do a write and an Fsync, but that's stupidly expensive. You can try doing this, also stupidly expensive. Why? Because you're paying the Fsync cost, which may have to clear unrelated buffers. And then this is what you would typically see using ODirect and ODsync, which basically says to the operating system, skip all the buffers in the middle, write it directly to the disk. And it tells the operating system, when you write it to the disk, I want you to turn on the FUA flag, force unit access, which means that the disk is requested to store the data in a durable format before it returns. This has a lot of limitations. You have to do it in a 4 kilobyte align mode. You have to make sure that effectively this is using direct memory access. It's very hard to do if you just writing a random application. But this already aligned so much to the way database thinks that this is very, very easy. It's important to understand that the commit actually happens when the log says, okay. And by the way, it's also possible that you got an error, but the commit actually happened because there was a failure after the commit succeeded. Something to understand is that you have, when you read the log, you have to protect yourself from partial writes. I started writing, then fell midway. Some of the data is in the log file already, but some didn't. So you typically have to sign the commits to the log to verify that they're okay. Something to consider is that we are writing to the log in a sequential manner. but we do not want to allocate the disk space for the log file automatically. Why is that? Because each time that we extend the file, we have to do fsync on the parent directory. Instead, we will typically allocate it in advance and then just run over that. In many cases, we are never going to read the log file. It's there only for emergencies. But the interesting question here, what happens when you actually need to replay the log? That means that you have to read and process process all of those changes, and then you have to update the disk, update the data file, which means that you have to read from the log in a sequential manner, but then do a lot of random writes to the disk, which means that this slows down your startup. This is especially the case if you're running on something like the cloud where I/O rates are typically abysmal. So we want to make sure that we don't keep too much in the log. And we'll touch on that in just a little bit. Now, because writing to the log is so slow, because we have to make a durable write, remember the whole point of all of these buffers is to pretend that the system is fast. We want to bypass all of those buffers and we have to pay that cost. So the idea here is that a user submit multiple transactions, and I can take all of these transactions, write them to the log as a single write. Each one of them is still atomic, but I can merge them into a bigger atomic aspect. Another thing that I can do, I have transaction 1, transaction 2. And this takes a lot of time, this commit. I can do this. When I start commit a transaction, I already start to speculatively execute the next one. This operates on this transaction data. If this fails, I'm going to have to revert everything. This very rarely fails. This gives me a huge performance boost in terms of the number of transactions per second that I can process. Now, let's talk about concurrency and transaction and how they work together. The easiest way to think about a database is with no concurrency. There is either read or write at one time. But the problem is that you tend to really have to deal with that. You can't really have a single-threaded database at this point. So you have to have a concurrent, and concurrency between reads and writes, plural, that matters a lot. We're coming back again to what is the protocol. If the protocol is a chat where multiple users may be holding up the line for a while and modifying data, that means that we have to support both reads and writes at the same time. If the model is the message that contain operation to do, we make it away with only having a single write. Now, why do I want to have a single write? Obviously, I want to have multi-threaded for better performance. Well, the answer here is quite different. If I have concurrent write transaction, I have to have locks. Locks are expensive. There is a really good paper called OLTP to the Looking Glass, who looked at the performance characteristic of various databases. Locking and latching in the database, basically ensuring that the concurrency is running appropriately, was over 30% of the time. By using a single-threaded writer, we get far faster results because we can spare a lot of those. And we can model concurrent write operations without concurrency using this approach. Concurrent transactions that are being merged into a single operation. That has a huge impact. That has a huge impact on performance. Now, I want to present to you something called MVCC, multi-versioning concurrency control. And this is how you can have reads that don't block writes and vice versa. So here, these are the pages in the file. And here I have a read transaction. It's currently read from page 4, page 8, etc. Then I have another transaction, and it wants to modify page number 4. So I'm going to use a copy on write. I'm going to take this value and copy it here, modify it here. And notice that now within the scope of this transaction, when I'm saying give me page 4, I'm going to go here, not here. This transaction still sees the old value because I haven't modified that. This transaction is going to do whatever it wants. Rolling back just means, oh, I'm just going to free this thing. When I need to commit, on the other hand, what's going on? I have something called PTT. What's that? The PTT is the page translation table. It's not transaction. Page translation table. And the idea here is that this is the PTT for transaction 13. When I'm looking for page 4, I'm going to look here. All transactions are still going to see the old value here. And let me see that with more values. So now we have multiple transactions that are currently running and modify the data. And each one of those modify the same page, and you can see that there are multiple versions of this page running all together. Now, the interesting about this, the old transaction 12, is still able to read old value. Each one of those is handling this independently. Now, here you have two read transactions that are looking at 14. So they're operating on the basis of this page translation table. What this means, by the way, is that no one, if those are the only transactions that I have, I know that no one is able to look at the value here. I can now write it to this behind the back. So when no one is looking, when all of the active transactions already have a PTT that include 4, I know that 4 in the disk is unused. So I can go and copy that from the scratch file, from the scratch buffer to the data file. And then I can update the PTT to remove the reference. And the new transactions will go to the data file. Yeah. So the whole idea in this case is that I'm running for atomicity. I only have to update the PTT, and then all of the changes that happen shows up as a single unit. Same with isolation. I'm not working on the same datasets. And durability, when I'm done with the transaction, I take all of the modified pages and write them to the log. Now, data file writes are buffered, which means that I have to call Fsync on the data file. After I called Fsync, I can go and trim the Rightahead log because I ensure that the committed transaction are already there. I can then also free the scratch buffers and make use of them. This is an example of MVCC using Postgres and RavenDB. With Postgres, you can see that it stores the data in this format. So this value is valid from this transaction to this transaction. This value is from this transaction to this transaction. Now, both cases, if I'm running this query on these separate transactions, I'm going to see the same results. But the way that it does that is very different. In this case, with Postgres, I would search here and says, oh, this is the relevant record. Because MVCC for Postgres works at the level of individual tuples. For RavenDB, which Voron is the name of the storage that we use, we are working at the page level. And the page level means that I'm saying transaction 18 is going to go here. And says, oh, here is Keynesian. Now, the reason this matters is that Postgres needs to go and vacuum the details. It suffers from the transaction ID, rollback issue, stuff like that. Voron doesn't have any of those issues because it just store all of the mapping at the page level. It does mean, however, that Voron and Raven uses more memory to represent that. But because of the transaction in Raven are typically much smaller, because RavenDB uses the message-based protocol, not the chat protocol, then this ends up being a non-issue for almost all cases. Now, I'm almost at the end, so I'm going to go quite quickly. We have to make a balance between disk I/O and computation. And in most cases, writing to the disk is so much more complex. So we do a lot of tricks to optimize that. We batch writes to the log with transaction mergers. But what do we write to the log? We write the modified pages. But why are we doing that? We have copy and write, so we at the end of the transaction we have the false and the previous and the current version of the pages that were modified. I'm going to apply a diff and write to the log only the different bytes that were modified. So if I modified one page, one byte in a page, I'm going to be able to write just one byte to the disk, to the log file. It's not exactly this way, but it's very, very close. Yeah. Other things that you can do, and I'm going to be done in just another minute. When you running through the B+Tree, you can predict what you're going to do and ask and already fetch additional pages. So mixing the I/O and the operation types. Another thing that is tend to be really, really complex is how you manage buffer management. How do you manage reading from the disk? How you handle all of that? And Postgre uses the TQ system. There are whole fields of research around that. This is complex. This is complex because you need to balance code needs, feature needs, what other things in the system happen. That's very hard. I cheat. I cheat by using mmap and telling the operating system, you get to decide what's going on.
Oren, I'm so sorry to interrupt you. I'm so sorry, but the time is over and I have to invite you to the discussion zone.
Yeah,
that's great because we're done.
We will definitely continue in the discussion zone. I see some members in the chat are there, so please join the Zoom. You have the link below the player, and we will go there. I will be there too. Thanks, Oren.
Okay, goodbye.